I want to first of all thank the organizers of this seminar series for giving me the opportunity and inviting me to give my a talk in my current area of research. So I thank you sincerely for the opportunity and the invitation. So the title of my talk is, as been announced, is Convergence Analysis of Fixed Point Iterative Scheme with Application. Okay, so I have the outline of my presentation. So in the first session, we're going to ask a question: why do we study iterative schemes? That's the first thing. We need to know why we study iterative schemes. What are the numerical features of iterative scheme? So what I've done is to make the talk to be as expository as much as possible, with the mind of trying to encourage some young academics to maybe perhaps develop interest in this area of research. So because of that, I try to put a lot of materials that are good, that we're able to look at some background information. So if the time is not there, I may skip the second session. The second session is all about some important nonlinear operators that are used in fixed point iterative schemes. So basically, we have the nonlinear single value maps that we do work with, and the nonlinear multi-value maps. So if the time is not there, I may skip the second section. So let's see how it goes. So I'm interested in the third sections where I introduce a notable fixed point iterative scheme. I'm going to start from pick-out iterative scheme, then I move to the what we do recent, what we are doing in the recent time. So I'm also going to introduce some nonlinear and optimization problems. So I tell you what we do in this area, and I'll give some recent iterative scheme that are being developed in the recent time. So the last session will be, sub-session will be one of my latest results and contribution with two of my students. Okay, so I've accumulated the organizer. So this is the abstract of the talk. So the first thing we want to ask ourselves is that why iterative scheme? So let me try to put this here. So I'll put it down. So the first question is why iterative scheme? So we need to know that iterative scheme are everywhere in computational mathematics. We can use iterative scheme to produce solution of certain nonlinear and optimization problem, which we are going to see in this talk. We can use it to approximate the fixed point of nonlinear operators, nonlinear maps. We can use it to find in this case, we approximate solution of constraint optimization problem, or we can design algorithm for sigma and image processing. These are the areas of applications. We can also use it to approximate zeros of complex polynomials. So that's why we study iterative schemes. So these are some of the numerical features of iterative schemes. Number one is the computability. So that is, we can use software like MATLAB to write code and run it with concrete data, and we can get our approximate solution. So we can do what we call the rate of convergence. So we want to look at the speed or the error estimate of iterative scheme, and we can also look at the stability of that iterative scheme. So here I have some important nonlinear operators that we use in fixed point iterative scheme. So we started a non-space S. I'm not going to waste much time here. So I'm most concerned in the third and the fourth. The third and the fourth section is where the key thing. So we start with a nonlinear space S. We have a mapping T that map S to X. So this map is called linear if it satisfies this inequality 2.1. So this L is called your leadership constant. So if your L is coming from this interval, so we call that mapping a contractive mapping, and it is strictly contractive if your L is from the open interval 0, 1. So in case in which your L here is 1, the map is called a non-expansive map. Okay, so we have an Hilbert space H. We have a map. T that map H to H. So this map is non-expansive. We satisfy this inequality 2.3. So the map is causing non-expansive. This is the fixed point set. F of T throughout means the fixed point set. So this is the set of all points that the map to itself. Okay, so if the fixed point set is not empty and inequality 2.4 is satisfied, so we call such a map causing non-expansive mapping. So it's finally non-expansive if it's satisfied, if you have inequality 2.5. And so we have what to call the non-spreading mapping. Let me see how to move this up a bit. Okay, so it's not spreading if it satisfies the next inequality. So we have 2, the norm of x minus norm of y to the power 2 is less or equals to t of x minus y in norm plus square plus norm of x minus 1 t of y squared. So this is equivalent, if you want to write it in terms of the norm and the inner product, so these two are equivalent. Okay. So that same single mapping is said to be k-strictly pseudo if you can get a constant k in 0, 1, such that for every point to pick in H, the Hilbert space you have inequality 2.6. So when the map is, the nonlinear map is k-demi-contractive if the fixed point set is not empty, and for every x to pick in H, this p is coming from the fixed point set, so we have 2.7. So T of P is just the same thing as P. Why? Because P is coming from the fixed point set. So P is in the fixed point set means that T of P is equals to P. So you can replace this T of P with P. So we have some inclusion. So what to find here is that as defined above, the class of Fermi non-expansive mapping is contained in the class of non-expansive mapping, and non-expansive, the class is contained in the class of quasi-non-expansive. So we have the most general one, which is the k-demi-contractive mapping. So it's more general than all the other mapping that we talk about. So if we have our operator T that is mapping the Hilbert space to itself, this operator T is called monotone if it satisfies the condition inequality 2.8 for every 2 vector you pick in the Hilbert space. So that map is called alpha strongly monotone. If you can get alpha greater than 0, such that inequality 2.9 hold for every point or vector you pick in H. So we have a case in which we call the map alpha beta equals strongly monotone. So if you can get a particular beta z greater than a constant greater than 0, such that you have inequality 2.10 that is satisfied. So what we have is that every Fermi non-expansive mapping is beta inverse strongly non-expansive. So this is just a case in which your beta is equals to 1. So if you make use of your triangle, if you make use of your Cauchy-Scott inequality here from this inequality, so you can easily see that every beta inverse strongly monotone operator is 1 over beta Lipschitz. So just make use of Cauchy-Scott inequality here, so you are going to get what I have here. This mapping is very, very important in our convergence analysis. That's what we call the metric projection. So the metric projection. So this is just a map. So in this case, you have a Hilbert space and you have a C, which is a closed subset of the Hilbert space. So this map, that map H to the closed subset of itself is called the metric projection. If for every point to pick in, if you pick a particular point SH, so we have PC of X, which maps that point into C if it satisfies this inequality. So which is called the nearest point to the point C. So mostly we make use of this property of the metric projection in our convergence analysis. So this says that so this point Z is the metric projection at a particular point X if and only if this inequality 2.12 is satisfied. So this is mostly used in our convergence analysis of trying to establish the convergence of the sequence generated by our iterative scheme. So another important properties of the metric projection is that it's a Fermi non-expansive operator. This is very, very important. This properties is also very important. We also make use of what we call the proximal operator. So the proximal operator is an operator. So we have a function f that maps H into R union. So you extend the real line with positive infinity. So the proximal operator on that particular function f with respect to the parameter gamma greater than 0 is the operator that satisfies this condition. So where I denote by argmin f, the argmin f is just the set of minimizer of this function. Set of minimizers of this function is what I call the argmin f. So that is the set of x in H, so that f of s is less or equal to f of y for every y in H. So invariably this set is just the set of the minimizers on this particular operator. So I have some useful properties of the proximal operators, which I have not wasted my time upon. So the mapping defined discussed so far are single value mapping. So we also work with some multi-value mappings. So here we have M, which is a multi-value mapping. So maps the Hilbert space to the power set of the Hilbert space, which is the set of all subset of the Hilbert space. So this multi-value mapping, M is called a monotone mapping. If you pick 2 points in H, you have U is in M of X and V is in M of Y, then we have inequality 2.30 be satisfied. So this other definition tells us when the monotone mapping is maximal. It is maximal on a condition that the graph of that map, this is the graph of M, is not contained in the graph of any other monotone mapping. So that is what it means for us to say that the mapping is maximal monotone. So we also have some other operators that are defined that are also multi-value. So this CB of H means that the set of all closed bounded subset of the Hilbert space. So this is a collection of sets, and the element there are closed bounded subset of the Hilbert space. So we have S mapping H to the set of all closed bounded subset of the Hilbert space. So this map is called to be Lipschitz or L Lipschitz if you can get L greater than 0. So this is what I call the off-dot metric, which I'm going to define in the next stage. So it's less or equals to L, the norm of X minus Y for every X. So if the L you pick here is in this interval, so the map is contractive. If L is 1, it's non-expansive. So the fixed point set, because this map in this case is a multi-value. So the fixed point set is just going to, if the fixed point set is not empty, and you have the off-dot metric of S of X, which is a subset of H, and S of P, which is a subset of H. But in this case, my P is coming from the fixed point set. So if it is less or equals to norm of X minus P, in this case, this map is going to be a constant expansive mapping. So we discussed a case in which the mapping is lambda demi-contractive. Okay, I don't want to waste too much time on my first section. So the resolvent operator is also very, very important. So let me skip the second section as I've said, so not to waste too much time. It's just to give some information about the kind of map we work with on in fixed point iterative process. So now I want to give some notable fixed point iterative schemes. So I'm going to start from the roots. I'm going to start from the good number of us have heard about the Banach contraction mapping principle, which is the pivot of metric fixed point theory. So I have some notable iterative schemes that have been modified in the recent time. So the first one is what I call the Picard iterative scheme. What is the Picard iterative scheme? So in this case, I have a metric space X. So X1 is the starting point. So I start with the starting point X1, which is in the metric space. So I define my Xn plus 1 to be T of Xn. So this scheme is what I call the Picard iterative scheme. So what do we know about the Picard iterative scheme? So I'm going to come with a Banach contraction mapping principle. So the principle says that if my metric space X is complete and the mapping T is a contraction, so I have two conditions on the metric space. Number one, the metric space is complete and the mapping T is a contraction. Then this mapping T, mapping S to X, we have a unique fixed point. That is one result. And the second result is that this Picard iterative scheme that you have in 3.1, we converge strongly to the unique fixed point of T. Is that okay? But we know over time that for mapping that are more general than the contraction mapping, one may not be able to apply the Banach contraction mapping principle. It doesn't work for such maps. So for example, the example of in the literature of some non-expansive mapping that the Picard iterative process may not convert to the fixed point, even when the fixed point exists. So for Picard iterative process, we go to another kind of iterative process, which I call the kind of SK iterative process. So what do we do here? So we pick X, which is T, a metric space. So we pick C, a closed subset of X. So we take the starting point X1 in X. So we define our iterative process as Sn plus 1 to be equals to half Sn plus 2 of Xn. T is mapping X to S in this case. Now you will discover that 3.2 generalizes 3.1. So what do we do? If you take your T in 3.1 in Picard iterative process, don't replace it by half into I plus T, then you discover that your 3.1 becomes 3.2. So it's just an extension of 3.2. Now what do we note? The set of fixed points of T, the same thing as the set of fixed points of I plus T. So that we know. Is that okay? So if you take X to be a nonlinear space in this tape, and you take your T to be a non-expansive, so we have the Krasnodębski iterative scheme, which generalized 3.2. So it's defined as you starting with a x1, start with x1, then you define Sn plus 1 as 1 minus lambda. Lambda is just a constant. It's just any constant greater than 0. Any constant greater than 0 is lambda. So you have 1 minus lambda xn plus lambda t of xn. So this is the Krasnodębski iterative process. So if we take your T in your Picard iterative process, you take your T to be T lambda, which is 1 minus lambda I plus lambda T. I is the identity operator on your nonlinear space. Then you discover that your KIP becomes your PIP. So you can see the correlation between them. So that means our KIP generalizes the Picard iterative process. Okay, we move further to what we call the man. So I just need to go to the basis, and you want to see how some of these iterative process have been developed or modified in the recent time to solve a good number of modern optimization problem. So now we go to what I call the man iterative process. So you will see reasons why we need to generalize or improve for some of these iterative process as we continue along. I will tell you the deficiency of some of these iterative process and why we need to keep improving on them and generalizing some of these process. Now, so we have what I call the man iterative process. So this one is on a Riemann space. So we have a Riemann space H. We take the starting point S1 in H. And so you define Sn plus 1 to be 1 minus alpha n Sn plus alpha n T of Xn. So this 3.4 is what we call the man iterative process. So what do we have? So if you take your T this time around, take your T of n as 1 minus alpha n I plus alpha n T n. Is that okay? So you discover that the fixed point of T and the fixed point of Tn is the same. Is that okay? So that's one thing you note. Another thing is that when you take your alpha is a constant to be the sequence alpha n. So in your Krasnodębski iterative process, if you take your lambda alpha, you replace it with a sequence, which is alpha n, coming from this interval, then you discover that your KIP becomes your man iterative process. So man iterative process is just KIP in a case in which this sequence alpha n is just a constant sequence lambda. So what do we have? The man iterative process only converges weakly in general. Is that okay? Now, but we also note that the man iterative process that it converges only to the fixed point of a continuous map, which is another thing. So however, if T is not continuous, then the man iterative process may fail to converge to the fixed point of T, even when it converges. So that is a shortcoming. That is a shortcoming to that. So after the man, we have in 1974, Ishikawa introduced his own iterative process, which also generalizes the earlier existing one. Now you also discover from what I've said that so if you take your alpha, if you take your lambda in your KIP, take it to be the sequence alpha n, so you have the man. So Ishikawa also tried to improve on man iterative process, and he came with this iterative scheme 3.5. So you have the starting point x1. So most of the time, Ishikawa is always referred to as the double man iterative process. So you have Sn plus 1. Sn plus 1 is 1 minus alpha n, xn plus alpha t of yn. But what is this yn? This yn is defined as yn is 1 minus beta n xn plus beta n t of xn, where you take n to be from the positive set of positive integers. So alpha n and beta n are sequencing 0, 1. Is that okay? So in case in which you take the beta n to be equal to 0, take your beta n to be equal to 0, you discover that your Ishikawa iterative process becomes your man iterative process. So if I take this one to be equal to 0, beta n to be 0, so yn is just 1. If your beta n is 0, yn is 1, so we just have exactly the Ishikawa iterative process. So Ishikawa iterative process is the man, sorry. So Ishikawa iterative process is just a generalization of the man iterative process. So then we have what we call the S iterative process. So in 2007, Gawa et al. Introduced this iterative process 3.6. But what we note is that the iterative process 3.6 is independent of all the other ones that we have discussed earlier. It's independent of the man iterative process, the Ishikawa iterative process, and the Krasnodębski iterative process. So what do we know about all this iterative process? they all converge weakly, and we are not interested in weak convergence. So this iterative process that I've discussed earlier converges weakly. But we know that if you are working in an infinite dimensional space, strong convergence are more desirable and interesting than working with sequence, the iterative process that converges weakly. So due to this, we need to then see ways of trying to improve on the existing iterative process to get those that will converge weakly in our infinite dimensional space. If you're working in finite dimensional space, there's no problem because weak and strong in that space is the same. When you're working in finite dimensional space, we don't have problem with that. But most of the real life problems are solved in infinite dimensional spaces. Is that okay? So because of that, APAN tried to introduce another iterative process. Fortunately, this iterative process converges strongly. So it's not weak convergence as we have in the existing one. So this iterative process converges strongly to a fixed point of a non-expansive mapping Hilbert space. So this is the APAN iterative process. So in this case, you have two starting points. So fix U, you pick a fixed point U from H, and you take X1 to be a starting point. So you define Xn plus 1 to be alpha and U. Look at this U plus 1 minus alpha and T of Xn. So whereby you pick alpha n from this interval 0, 1, the close interval 0, 1. So the good thing about the APAN iterative process is that it converges weakly. That's fine. So, but we also look at the rate of convergence is also an issue. So after the APAN iterative process, we have another iterative process developed by Zhu. So the difference between this and the APAN one is that the APAN one have alpha n u. So what who did here is to replace U with f of xn. So the difference between 3.8 and 3.7 is that you just replace your U in 3.7 with f of xn, where f is a contractive mapping. That is not the difference. That is not the difference between the viscosity iterative process and the APAN iterative process. So in APAN iterative process, take your U and replace it with f of xn. So what is the advantage? The advantage of the viscosity over the APAN? The advantage is that the viscosity have a better rate of convergence. That is the advantage. The advantage of the viscosity iterative process by Zhu is that it has a better rate of convergence. That is the advantage of that. So these are some of the earlier iterative processes that we have. But in the recent time, several authors have tried to modify. So that's why we see this, we have APAN type, we have viscosity type. So in the recent time, authors have tried to modify, some of the earlier existing iterative process to get a better rate of convergence and to use this to approximate fixed point of some nonlinear maps and also approximate the solution of some optimization problem. So there are two things we do with this iterative scheme, which I'm going to tell. So one of them is to approximate the fixed point of a nonlinear map. The second thing we have discovered in the recent time is that we can also use this to approximate the solution of some important optimization problem. So as you go along the talk, you go to see that approximating the solution of some important optimization problem is equivalent to approximating the fixed point of a particular nonlinear map. So I'm going to establish this as we go along the line. So this is another iterative process by which I call the proximal point iterative process. So this basically is used to solve what I call the minimization problem. So the minimization problem is an important optimization problem. So what is this problem? So you recall what the minimization problem is all about. So you have a function f that map H to R. So this function is convex and is defined as, so the minimization problem is defined as you want to find x star in H such that f of x star is less or equal to f of y for every y in H. So this is an optimization problem called the minimization problem. This x star is called the minimizer of f. It's called the minimizer of that function f. So it minimizes the function f. So throughout, anywhere you see admin of f, I take admin of f to be the set of all the minimizers of f. So the set of s in H, so that f of s is less or equal to f of y for every y in H. So this is the set of all minimizers of f. So one of the earliest iterative process developed to solve the minimization problem is the proximal point algorithm, so which is given in 3.9. So we take a starting point S1 in H and you define Sn plus 1 to be the admin of, so admin over Y in H of this, what we have here, f of Y plus 1 over 2, mi of N, the norm of Y minus Xn to the power 2. So one of the disadvantages of this proximal point algorithm is that it only converges weakly to the minimizers of F. It doesn't give a strong convergence. That is the shortcoming. That is the shortcomings of this proximal point iterative process. So a question was raised by Rockefeller, and the question is that is it possible for the proximal point iterative process to converge strongly, or the only thing we can get is reconvergence? So this question lingered for a period of time before Gula was able to produce a counterexample to show that really the proximal point algorithm does not converge strongly. The best you can get from it is weak convergence. So what do we have from there? So that shows that we need to add some additional condition on F, or on the other end, or the space in which we are working with for PPA to converge strongly. So we want strong convergence, because when you're working in infinite dimensional space, we always desire to have strong convergence, which is better than weak convergence. But if your space is finite dimensional, you don't have problem with that, because in that space, we can strongly be the same. But in infinite dimensional space, the two of them are not the same. So most of the real life problem we solve are not sitting in infinite dimensional space. So, and because of that, here, we are more interested in getting algorithms that will converge strongly in our space, if the space is not finite dimensional. Okay, so the PPA39 was later generalized to what we call the APAN type PPA. APAN type PPA, with the mind of trying to get the strong convergence of the minimizers of F. So fortunately, Kamimura and Kakahaski were able to try to modify the proximal point algorithm to have the APAN type. APAN type is a type of APAN algorithm that I've earlier discussed. Unfortunately, the sequence generated by the Accretive algorithm converges strongly to the minimizers of F. So since then, there will be different modification of the proximal type point algorithm to approximate the solution of minimizers of F. Okay, so let's go to some nonlinear and optimization problem. So what we discussed so far is all about the fixed point of nonlinear operators. But what about optimization? So optimization problem here includes the one that I've just talked about, minimization problem, variational inequality problem, which I'm going to introduce briefly in the next, maybe in the next 1 or 2 slides, the equilibrium problem. All these have a lot of applications. The monotone inclusion problem, among others. These are known to be very useful in diverse fields. You can use them in ecology, in physics, in economics, in computer science, in engineering, and you can use them a lot. So because of that, because of its usefulness and effectiveness of one of the most useful, there are several ways of solving your optimization problem. Let me point that one out. You can solve it several ways. But one of the effective methods of solving optimization problem is the fixed point approach, the fixed point method. The fixed point method is one of the effective way of solving it, which I'll show you. So as a result of this, a lot of research efforts have been devoted in developing different fixed point iterative algorithms for approximating solution of optimization problems. But one thing, the key thing that I want you to go on with is that in general, approximating the solution of optimization problem is equivalent to you finding a fixed point or approximating a fixed point of a suitable nonlinear map. Is that okay? So you try to approximate solution of most of the optimization problem we work with is the same way, it's the same thing, or it's equivalent to you trying to approximate the fixed point of a suitable nonlinear maps, which you will see as you go along in the last. Okay, for instance, a solution of the minimization problem that I've discussed above is the same thing as the fixed point of the resolvent of the converse function associated with the minimization problem. Also, if we want to approximate the solution of monotone inclusion problem, which I've discussed later, The solution is the same thing as the fixed point of the resolvent of monotone operator that is associated with the monotone inclusion problem. So what do we conclude from that? So we have this conclusion that solving optimization problem, this is the key thing. Solving optimization problem is concerned with developing different iterative algorithms for finding fixed points of resolvent of mapping that are associated with this optimization problem. So this is the key thing. This is the key thing. This is the key thing. Okay, so let's discuss one or two or three, introduce one or two or three this optimization problem. So one of them is what I call the variational inequality problem. The variational inequality problem. So in this case, you can define it in an Hilbert space, you can define it in a Banner space. And in the recent time, optimization problem is being solved in some other important spaces like the Adama spaces, which is a complete zero spaces. So I think we have done one or two work in that direction. So this E can be your Banner space, can be Hilbert space, can be some more generalized metric space. So we have C. This C is always a non-empty closed convex subset of the Banner space or the Hilbert space. So a variational inequality problem is defined as you finding a point S star in C. That's the key thing. You are finding a point S star in C such that this inequality 4.1 holds. You want to find a point X star in C, point X star in C. You want to look for a point X star in C such that the inequality 4.1 holds. So that is what variational inequality problem is all about. So we have your A is mapping C to the dual space of E. So E can be Hilbert space, can be Banner space, can be Adama, some other important spaces. Okay, so we denote the solution of the variational inequality problem by VIC. So this is what we denote the solution of the variational inequality problem by. So the four general theorem for the existence and uniqueness of solution of variational inequality problem was proved by these two authors in 1967. So since we know that the solution exists, and so since then there have been several work in trying to approximate the solutions of the VIP in the recent time. Okay, so another important optimization problem we work with is what I call the equilibrium problem. So that is what I call the equilibrium problem. So in this case, you have what I call the bifunction. So C, so you can define your equilibrium problem in Hilbert space or in Banner space. So C is always a closed convex subset of the space in which you're working with. So we have what I call the bifunction, which maps C cross C to R. It's a bifunction. So your equilibrium problem is defined as you want to find a point in C. You want to find a point in C such that f of x comma y is greater or equal to 0 for every y you pick here. So find a point x in C such that this inequality holds. Is that okay? Before you can solve the equilibrium problem, I think about 5 assumptions are needed to solve that. I don't want to bother you with the assumptions here. So what I've done here is just basically to tell you what equilibrium problem is all about. And I want to tell you that the solution have been established to exist. Solution have been established to show that it exists. And since the solution exists, and then there have been in the recent time several iterative process developed to approximate the solutions. And apart from that one, the equilibrium problem have also been generalized. So now have what we call generalized equilibrium problem, the mixed equilibrium problem, and so on. So one of such generalization is the following. So we still have our bifunction. So here, two other maps are introduced. Is that okay? So we know what in our equilibrium problem, we only have this bifunction F. So we have another problem, optimization problem called the generalized mixed equilibrium problem. So in this case, we added two more maps. So we have the map, we added the map H that maps C to E. We also have the map C, map phi that maps C into R. We extend it to the positive infinity. So the generalized mixed equilibrium problem is just you finding a process in C such that inequality 4.3 holds. Is that okay? But you discover that if your phi is equals to 0 and H is equals to 0, generalized mixed equilibrium problem becomes your equilibrium problem. So this is to what you have in 4.2. So if your H is equals to 0, so this part is gone. If H is equals to 0, this part is gone. So we only have this with this greater than 0. So the problem becomes what I call the mixed equilibrium problem. The mixed equilibrium problem. And so if your phi is equal to 0, H is still there, so the problem becomes generalized equilibrium problem. And if both H and phi is equal to 0, so it reduces to our standard or classical equilibrium problem. So the solution of this problem have been established to exist, and there have been several iterative methods. It's an ongoing research to approximate the solution of some of these methods, some of these problems because of their importance. So now the fixed point problem. So what is the fixed point problem? So you have a nonlinear map, can define it on Hilbert space, on Banach space, on metric space, whatever. So depending on the space you're working with, so we have a nonlinear map. So this point X I've defined earlier, the point S in E is called the fixed point of T if it mapped, if T is mapped X to itself. So, but this is a case in which your map is a single value. But if your map is multi-value, so that means T is mapping to the power set of E. So X in E is called the fixed point if X is in the T of X. You know, the T of X is going to be a subset of the subset of E. So in case your S is single value, so S is the fixed point of T, X is equal to T of X. If I'm working with multi-value, S is called a fixed point of T if S is in T of X. So we denote, as I've said earlier, instead of fixed point of T by F of T. Is that okay? So in general, I keep repeating this. Finding a solution of optimization problem is equivalent to solving fixed point problem. That's it. Finding a solution to an optimization problem, this equivalent is very, very important. It's equivalent to solving fixed point problem. That is, you are approximating the fixed point of a particular nonlinear map. Okay, so another kind of problem that is used in another kind of problem that is also very, very important and popular is what I call the split feasibility problem. It's an inverse problem. It's an example of an inverse problem. Okay, so in this case, we have two inverse spaces, H1 and H2. H1 and H2, we have a Monotone operator that maps H1 to H2, and C is a closed convex subset of H1, and Q is a closed convex subset of H2. So we want to find a point X in C such that A of X star is in Q. So this problem of this kind is what I call the split feasibility problem. And so in the recent time, we have seen a lot of iterative algorithm developed to approximate the solution of this one. Why did we solve this? We have seen that over time, we have proved in literature that split feasibility problem has a lot of application. For example, we can use it in medical image reconstruction. We can use it in intensity modular and modulated radiation therapy treatments. So because of its application, a lot of work is going on there. So here I talk about the relationship that exists between these three optimization problems. Let me go down. So there's a connection between the variational inequality problem, the split feasibility problem, and the fixed point problem. So what is the connection? Look at the connection, which is very, very important. So now you assume that the split feasibility problem is consistent, meaning that the solution set is not empty. The solution set is not empty. Now we have X. Solve this feasibility problem is equivalent that to X solving this fixed point problem. So you take this as a map. So you take the whole of this as a map. So it's mapping S star to itself. So S star solve this fixed point problem, this split feasibility problem. It is saying it's equivalent to S solve this fixed point problem. It's also equivalent to F solve this variational inequality problem. So you see the connection between the two of them. Solving this split feasibility problem is equivalent to you solving this fixed point problem, and it's also equivalent to you solving this variational inequality problem, which is a very important result that we have used in the recent time. So because of time, let me go to the last section because it's almost time. So let me see how to round up in the next 5 to 7 minutes. So let's quickly talk about the recent development. So in the recent times, several authors, it's still an ongoing, still a very active area of research. That in the recent times, several authors have studied the above iterative process. And what they have done is so far is to modify, to generalize, to make sure they get a scheme that converges. They try to work on the rate of convergence, error analysis. So in the recent time, we have seen a lot of generalization or modification of the earlier iterative process that I've discussed above to approximate the fixed points of nonlinear maps. And invariably, approximate the solution of some important optimization problem in either Hilbert space or in Banach space or some other important spaces. So this area is an active area of research with numerous research articles in literature, numerous of them, which are mainly published in these journals. These are specialized journals in fixed point theory. One of them is Journal of Fixed Point Theory and Application. This is a Q1 journal. This is a Q1 journal with a good high impact factor. So all these journals are journals that are devoted to fixed point theory and applications, fixed point theory and application to optimization problems. So these are important journals that most of the research work in this area have been published. Almost all the journals here in Q1, except one or two of them that's in Q2, that are Q2 journals. Okay, so let me quickly talk about my contribution, one of our contributions. So I only have about 3 or 4 slides here. So let me quickly talk about one of our latest results. So what we have done here is to propose a new method for solving split variational inequality problem without the co-coercive condition. So if you want to get a copy of this article, so you can I put the link, or you can just type this this DOI number, you can get a copy of this. So this was published in last year in the Journal of Fixed Point Theory and Application. So this was published last year in the Journal of Fixed Point Theory and Application. This was done with two of my students. So this was published last year in 2020 in Journal of Fixed Point Theory and Application. So if you need a copy of it, I think you can get it using this DOI number that I've put there. So here, what we have done here is to propose a new method for solving a split variational inequality problem without this condition, the co-coercive condition, which is very restrictive. So this condition, most of the iterative algorithm in literature to approximate the split variational inequality problem have this co-coercive condition. You see what it is. So what we have done here is try to eliminate. So and this condition restricts the application and the usefulness of the iterative algorithm. So what we have done here is to remove this condition. And we're able to establish a strong convergent result. So as I've said, so in solving a split variational inequality problem in Hilbert space, the co-coercive assumption of the underlying operators is usually required. And this limits its usefulness, the usefulness of the iterative algorithm and its application. Limit the usefulness of the iterative algorithm. So to have this operator free of this restrictive assumption that I said, so what we have done in this paper is to propose a method for solving the split variational inequality problem in 2 Hilbert space without this assumption. So that's what we have done. So we proved the strong convergence of the iterative. So we are fortunate to get a strong convergence of the iterative algorithm that we propose. We also try to compare our methods. So yeah, in the recent time, so when you propose an iterative algorithm, you must try to compare with 2 to 3 to 4 to 5 other existing algorithms to be sure that yours perform better. Because there's no point you just propose an iterative algorithm that already have an existing algorithm that perform better than it. So when you propose in the recent time an iterative scheme, you must be able to give some numerical examples. Give some numerical examples to show, to establish that yours perform better than 2 or 3 or 4 similar existing ones. And this we have done here. So we prove the strong convergence of this iterative algorithm that we propose, and we give some numerical example to illustrate the performance of our method. We also compare it with some related method, and we're able to show that ours perform better. Okay, so I talk about this co-coercive operator, this co-coercive condition. So what is this all about? So let's look at what it is. So we have our Hilbert space H. We have A mapping H to H. So this A is said to be L co-coercive, which is the same thing as L inverse strongly monotone. If you can get a constant greater than 0, so that this inequality is satisfied. This is straight for way to establish our strong convergence. So, and then what we have done in our work is to take away this condition. So the mapping A is monotone if it satisfies this condition, it's Lipschitz if it satisfies this condition. So if we make use of the Cauchy-Scott inequality here, mix of Cauchy-Scott inequality here, so you can see clearly that the eco-coercive operator is 1 over alpha Lipschitz continuous and monotone, but the converse is not true. The converse is not true. So that is why our method is better, because the converse is not true. Okay. So our proposed method rests on the following assumption. So we're able to prove our strong convergence using the following assumptions. So we have two feasibility sets. So C is a closed convex subset of H1 and Q is that of H2. So we have mapping A, mapping H1 to H1, and mapping F, mapping H2 to H2. These are both monotone and Lipschitz continuous, and this is their Lipschitz constant respectively. So we have a nonlinear maps that connect H1 to H2. So whenever you are solving split problem, you must always have a nonlinear map that connect the spaces together. So what you have is that you have two variational inequality problem. So the first one, VIC, is a solution of rational inequality problem in the operator A1, with the operator A1 in H1. And VIFQ is the set of solutions of the rational inequality problem in the space H2 with the operator F, So we have a split problem. So how do we define the split problem? The split problem means that the solution of, we are finding dz in, which is the solution of the first rational inequality problem in H1, such that the image of this z, under this linear map, is the solution of the second variational inequality problem in the space H2. So that's why we call it a split problem. Is that okay? So we have this. So we have our put condition, our control parameter. These are the conditions. So how do we define our proposed method? So we have to start with the initialization. So we take tau to be a constant greater than 0. We take lambda. So you must know what this L1 and L2 is. So this is the co-cohesive constant of F. A and the co-cohesive constant of F. So we take lambda here, we take, so we don't want co-cohesiveness here. So lambda L1 is the Lipschitz constant of A because our two operators are only Lipschitz continuous. They are Lipschitz continuous. So that means L1 is the Lipschitz constant of A and L2 is the Lipschitz constant of the second operator, which is F. So how do we define the iterative scheme? So we start with the starting point H1, S1, which is in H1. So we define Sn plus 1 as follows. So this is how our Sn plus 1 is defined. So we have the first step, which we define, we set our Yn to be this, and we compute Zn. So this is our step 2, step 3. So what do we have here? You see, we have a projection map here. So this one solves the second variational inequality problem in H2. And this solved the this Xn plus 1, which is also related, Sn plus 1, where is it? Sn plus 1, which is also related to UN, solve the variational inequality problem in H1. So we got two projections here, projection maps, because some of the existing methods of solving this problem are the extra gradient method. Extra gradient method means that in solving the variational inequality problem, you have two projection methods, and this is not good because you need a lot of time to be able to get the convergence of such sequence. So if you can get an iterative method that uses only one projection, that means that result is better than having two projections. So what you have is that we have one projection in each of those, in solving each of the variational inequality problem. So we have this. We have the step size. So this is the step size, gamma n. It's how we define our step size. We also have another step size here. So we have two step sizes. Okay. So what do we have in our the motivation and the novelty of our method as discussed? So why is our method better than the existing one? One of this is what I've said earlier, that we have tried to remove the co-cohesive conditions on the operator A and F, which restrict the applications of the existing iterative algorithm. So which is the novelty, one of the novelty of our result. Another thing is that the earlier way of solving the VIP used the extra gradient method. Extra gradient method means there are two projections. But here, we have two variational inequality problems being solved, one in H1 and the second one in H2. Is that okay? So we solve two variational inequality problem. We use a binary linear map from H1 to H2 to connect the two solutions together. So what we have seen is that our method can be viewed as a single projection method for solving the VIP in H1 and a single projection method under a binary operator T for solving the other VIP in H2 with no extra projection, either on the out space or on the space, which is an improvement over the existing one. Okay, and the second advantage is that we have taken the co-coercive condition out. And another one is that our iterative algorithm does not depend on the norm of the bounded linear operator. So we choose our step size in such a way that the step size does not, the step size is the tau n, it does not depend on the norm of this operator, because sometimes this norm can be difficult to find, or sometimes it's not even possible to find it. So these are the theory improvement of our result over the existing one. So the key result we have here is that, number one, we have this lemma. We show that the sequence that I've defined above is bounded. So you must show that the sequence is bounded before you show it converges to the solution in the space. So the first thing we have is first lemma is that we show that the sequence is bounded on the assumption that I've given earlier. And the main theorem is that the sequence converges strongly under these assumptions with the one we have earlier. So the solution in gamma. So what is the gamma? We have already told you what this is all about. This is just the solution space. This is our feasibility solution set, which is the set of solutions of the split rational equilibrium problem. And the additional advantage is that what it converges to, number one, is a solution to the problem we are solving. It's also solve the minimum norm problem. Is that okay? So the norm of our solution is the minimizers. Is that okay? Of the norm of the minimizer of the set of points in that solution space. Okay. So the result here and the proof of this lemma and this main result with other result that we established can be found in this paper. So if you are interested in this paper, if you contact me, I can send the private copy to you, or you can also, if you have access to this journal online, it's already published, so you can get a copy of that journal. I think my time is over, so thank you for listening. I'm going to rest my case here. Thank you very much.